Hello again, this is Jody Matos, and in this video we'll talk about chapter 5, arrays, now going into problem number 5.2, which is about incrementing an array, incrementing an arbitrary precision integer. So the idea behind it is that certain applications require arbitrary precision arithmetic, and one way to achieve this is to use arrays to represent integers. So fundamentally, each position in the array represents one digit of a number, and with that you can represent a number of any precision you need to, right? So the idea with this problem is write a program that takes as an input an array of digits encoding an integer, a number n, and updates the array to represent the number n plus 1. So given an example here, considering a number 129, the array to be given as input is a 3-sized array with the digits 1, 2, 9 in this order, and then the output is the number 130, but then after incrementing the input number. So that's the idea. So let's get to our coding. Int as array increment.cc is a file we want to play with. So let's go into it. All right. Int as array increment. This is the file. Let me make sure we have everything we need to start coding it. Let me return the same empty vector for now. Let me make it to make sure we're compiling the right file. We are. It's currently erroring out with the exact example we just discussed. So this is the moment of the video that I invite you to pause and try to solve it on your own. Okay, so I assumed you paused it and tried to solve it. Now let me dive a little deeper into two approaches that we can discuss about how to solve this problem. So first of all, let us understand what we have in hand here. It's a +1 function that receives as an input a copy array, a vector of integers called a, and then that's the array you expected as an input, and then we're expected to provide as an output a return to a vector of int as well, which is now the a plus 1. So with that in mind, there are two approaches I wanted to discuss about this. I didn't prepare any slides for that because the two of them are pretty much straightforward. For the first one, we're going to follow a 3-step approach. Okay, let me just clarify that. First one, we're going to build the number from the array. So fundamentally, we're going to convert the is a like brute force approach. You're going to convert the vector that you received into a number itself, like an integer. But as we're talking about potentially pretty big numbers, like I'm going to use an unsigned long, because there was no discussion about having it signed like a negative number. Then once we build that number, we're going to increment the number using this type that we just created, and with that we're going to rebuild the array. Well, this idea is not going to work very well because again it doesn't solve the problem, because now we're going to be limited by the number of digits, or by this maximum number that could be represented by the unsigned long in the compiler you're using on your end. You can look it up on the web if you want to understand what is the biggest size that it can be represented in this nowadays with the compilers you're using right now. But I wanted to exercise this flow so we can see the problems, and also for us to understand how that could be. It can even help you solving all the types of problems down the road. So again, we're going to take the array, we're going to build a number out of it, then we're going to increment that number, and then we're going to rebuild the array after that. Right, so let's dive in. First, to start building the number, let me create a variable, unsigned long number. Yeah, I'll start it with 0. And I'll also, in order to create the number, I'm going to multiply it by a factor, so that we can go from the rightmost digit, and multiply that by the ones position, then the tens position, the hundreds position, and so on and so forth. I'm going to start that with a factor. I'm going to use again an unsigned, but now an int is enough, I guess, which is going to be my factor. I'm going to call it, I'm going to start with 1, so I can multiply with the 1's position, right? And fundamentally, the idea is that we're going to have, for the build number step, let me start it from here, we're going to have a for loop, so for int, let me call it I, starting from a dot size -1. I'm starting from the rightmost position, and then I'm going to proceed with that as long as I is greater than or equal to 0, and then I'm going to decrement I at every iteration. So that's my for loop, and at every iteration of the for loop I'm going to build a number, which is going to be number plus equal, so just going adding them up, a at the position I, so the ith index, or the ith value in a, multiplied by the factor, which is the first value is going to be 1, right? So that helps me build up the number. But then before ending the loop, I need to make sure that my number is now multiplied, my factor, I'm sorry, is multiplied by 10, so that I start with the ones, and then the tens, and then the hundreds, and thousands, and so on and so forth. So that's the idea. With that, I am building up the number itself. Now I can increment it, so I just take plus plus number, right? So with that, my number is now incremented, and with that, now I need to rebuild the array. So in order to rebuild the array, let me start with just some basic assumptions. All you need to do is to find the position for the rightmost index for your array, and that's obviously dependent upon the size of the number after it's incremented, right? So one way you can look it up if you want to, but one way you can find the position of that digit is by using the log10 position. So I'm sorry, the log10 function fundamentally is 10 to the power of this value you're going to find equals to the number, right? You want to find, and the idea is if you have like a 2-digit number, let's say 29, 10 to the power of 2 is what you're trying to find by using a log10 array, truncating the result of the log10 function into an integer, right? So that's the logic behind it. You can look it up if you want to. I'm not spending too much time on this discussion about this, just because I want to dive into the implementation of that. But again, the digit place you're going to start to is a log10 of number. Again, log10 of 30 would be 3. Log10 of 39 will be something around 3.9, like high, close to the 4s. But again, notice that we are truncating this into an integer. So let me even add a comment here just to make sure. Truncating to act like a floor function of some sort, right? So that's the idea. Now we have the digit place for the first value in the array. Then I'm going to have a while loop. So while digit place is greater than or equal to 0. That's what I'm going to try and do, right? I'm going to start calculating the value for the digit place position. Digit, oh my goodness, digit place position equals to number, and the I always get these words confused, the remainder and reminder. The remainder of the division by 10 goes to the array position itself, and then the number now is divided by 10, right? So number divided by equals to 10. So what that means is when I do this, I take the rightmost position of the integer, in this case of the digit place, I'm sorry, of the number in this case, which is in an unsigned long. I take the rightmost digit and put it into digit place, and then with that I take everything else but the rightmost position and keep it in number, right? That's the logic that's been used. I'm consuming fundamentally the rightmost digit one at a time, And then all I need to do after this is to decrement digit place, so I can go to one position to the left. I can do all that right here by using a decrement operator right after it was being computed. So that is the logic behind it. Once all that is finished, I can just return A. So with that, there are two problems here that I wanted to discuss. First, the first one is the one we already discussed, we talked about, which is what if the number is really big, and then it goes beyond the number that can be represented by an unsigned long, and then this approach would fail. But the other problem is, let's say you have the number 99, right? You have the number 99. We are starting with an array of 2 positions. The 99 should become 100, and the 2 positions should become 3 positions. And in this approach, we're not checking if there is a carry out that goes beyond the size of the array. So that's a problem, but let's just see what happens if our unit tests in this case can catch this problem. Let's compile it. No compilation problems. Okay, it solved the first one, and it errored out in the second one, which is exactly 9,999, right? And the expected results is 10,000. But then, as we didn't update the size of the array, that was the result we had, right? So one way we can solve this problem is just by checking, hey, if digit place is equal to the size of the array. So again, what I'm asking with that is, once I compute the digit place and I see that it is the same as the size, which means that it doesn't have enough space for that guy, all I need to do is to insert insert in the first position. So a.begin. I'm going to insert digit number 1, because with that, then my computation will be correct. I'll shift things right and add 1 in front of the computation, and then that will give me the number I want to. Let me make it up again. And it now solved the first 5 examples or tests in my regression here, but look at the size of this input. Oh my goodness, how big is that? Let us check. Once we are here, let me just print I don't know, std. Yeah, just something that we haven't done before. I wanted to expose that to you guys. You can debug things as you are trying to solve it in the system, right? So std, I want to print a.size, and then I'll print a.size. Oops, a.size, and then I'm gonna print end line here as well. std and l. I think I'm gonna even add an end l in the beginning too, just to make sure that I'm not leaving anything behind. All right, I think that should do it. Let's see the size of all solutions right now, and then on the 6th one I'm gonna see. There you go. A.size in the beginning was 3, 4. So far so good. This guy has 65 digits, obviously not represented or not representable by an unsigned long, and that's where this solution doesn't work. Let me just add here a comment, and the first version doesn't. Well, let's take a look into time and space complexity. This comment can go away, but let's leave it there. All of these are constant in time. We have a for loop by the size of the array, so we have some iterations here, but at every iteration we have constant time operation. So far so good, all constant time. And then here again another while loop, but again only as per the number of digits in the number. So considering n, the number of digits in the array, I'll say that time complexity is O of n, and space complexity is O of 1, right? Okay, but then it does not solve the problem, right? So for the second version then, the approach you're going to follow is fundamentally the same approach we do, any basic arithmetic in school, right? This is the sum of two numbers. We're gonna increment the rightmost number, and then just carry the overflows and the carryouts, right? Take care of the overflows and carryout. What does that mean? If I increment the rightmost number, okay, the overflow means that given number went from 9 to 10. That's exactly what it means. We're only incrementing it by 1 anyways. So that's the only case we're going to have an overflow. So I check if that number is 10, then I replace that one with a 0, and then increment the one to its left. And I go repeating the process, trying to replace every 10 that I get on the way, as long as the number that I'm processing is different than 10. That's the overall idea. That's exactly how we're supposed to do that in school, or learn how to do that in school. And then let's implement it this way, right? Again, let's start by incrementing things from the right. So let's increment a dot back. Know your functions in the vector class, right? So a plus a dot back is going to increment the rightmost number. Now we're going to have a for loop, int I starting from a dot size minus 1, and we're going to stay in this loop for as long as I is greater than or equal to 0. Greater than 0. We're going to see that in a bit, why that is the case. Then I only continue for that as long as a of y is equal to 10, because if the digit is not 10, I'm done already. I don't need to do any other carry out. That should stop right there, and I can stop my for loop. That's the idea. Okay, and then in this for loop, all I need to do is now I already know that a of I is equal to 10. Then I need to say, hey, a of I now is equal to 0, and then I increment a of y minus 1. So that's why I cannot go all the way to 0, otherwise I'm going to increment position minus 1. So I take this guy and I increment it. So I can do that before. Okay, that does the trick, and that should increment all of it, except in this case it doesn't handle like the 99 that goes to 100, right? So let's take care of that as well. Whenever we get to this, then after all that, if a of 0 is equals to 10, which means I already incremented them all, in the first position in the array is equals to 10, which means that I also need to take care of this extra carry out. The way to do it is the same idea. A in position 0 is equal to 0. Oh, that should have been an assign, not a Boolean operator. So a in position 0 is now 0. And then I will just insert a 1 in the front. It's as same as I did before. A dot insert in the beginning of the array. So a dot begin, position number 1. I'm sorry, value number 1. That should do the trick. Then after that, I return a. That is it. Let's see if it resolves all the cases. There we go. It did resolve all the 505 cases that we have in the system. So that's the idea. Let's now review time and space complexity. So a dot back is constant in time. We have a for loop here that iterates worst case scenario once per position in the array. For every iteration, we only have constant time operations. Then we have one extra constant time operation in this right shift here. We can have an O of n plus 1 here, because we're going to shift every position to the right and then add one more. Again, O of n plus 1 here, which is also O of n. So that's the idea. So for time complexity, this is O of n, and then for space complexity, this is also O of 1. So, and this one does solve the problem. So that's the idea. If you thought of something different than that, please share. But again, these were the two approaches that I came up with, and pretty good in terms of exercising the idea behind arrays. But now, in the next one, we're going to see something that is somehow similar to this, but a little more tricky. So thank you again. See you next time.